Imagine traveling from New York to Los Angeles in about 20 seconds, or from London to Rome before you have time to unlock your phone. That is roughly how fast the Parker Solar Probe can move at its peak speed. It travels at about 191 kilometers per second, making it the fastest human-made object ever built. That number sounds almost unreal at first. 191 kilometers every single second feels beyond ordinary experience. At that speed, cities blur into moments and continents feel small. It stretches the imagination in a way few numbers do. And yet, even moving that quickly, a spacecraft would still take thousands of years to reach the nearest star. The nearest star system, Alpha Centauri, is more than 4 light years away. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. When we place these numbers side by side, scale begins to shift. Light travels more than 1,500 times faster than our fastest spacecraft. Even the fastest probe ever built moves at only a tiny fraction of light speed. That difference shapes everything that follows. So when we ask how far we could travel using the latest technology, we are really asking something deeper. We are asking how distance works in space. We are asking how speed and time connect to one another. And we are asking how long a human life feels when placed inside that scale. On Earth, distance feels manageable. You can drive across a country in a few days. You can fly across an ocean in less than a day. Even the longest journeys still fit inside a calendar week. Space does not shrink that way. The Moon sits about 384,000 kilometers away from Earth. Mars can be tens of millions of kilometers away depending on its position. Jupiter rests hundreds of millions of kilometers from us. Beyond the outer planets, the distances continue to grow quietly. Pluto orbits billions of kilometers from the Sun. The Kuiper Belt stretches even farther. And beyond that lies a distant region of icy bodies that may extend tens of thousands of astronomical units outward. A human life adds another layer to the question. If someone launches at age 30 and lives to 80, that gives about 50 years of travel time. 50 years feels long in daily life. In space, 50 years can pass while a spacecraft remains inside the Sun's outer influence. Travel in space depends on more than bravery or ambition. It depends on fuel mass, engine efficiency, and the energy required to push a spacecraft faster. It depends on how long life support systems can operate and how well a crew can endure isolation. It depends on physics, which sets quiet boundaries around every mission. Most spacecraft do not continue accelerating forever. They receive a powerful push at launch, then coast for years. Gravity assist from planets can add speed, but fuel remains limited. Once the engines fall silent, momentum carries the craft forward. So the true question becomes clear in a gentle way. Using the propulsion systems we already have, or those that are close to being tested, how far could we really go? How far could we travel in one lifetime? How far could we travel if we never turn back? To answer that, we must measure speed against distance. We must compare kilometers per second to millions and billions of kilometers. We must compare years of travel to light years of separation. Only then does the boundary of our reach begin to take shape. The universe does not resist us with force. It simply stretches outward with extraordinary size. And once that size settles into the mind, the question changes from how fast we are to how vast space truly is. Space uses units that can feel distant and abstract at first. Numbers become so large that they stop meaning anything to the imagination. 1,000,000 kilometers sounds impressive, but it is still difficult to picture. So before we travel outward, we need a simple way to understand scale. The first step is remembering that distance in space is usually measured in kilometers. The Moon is about 384,000 kilometers away from Earth. That number already feels large, yet it is small compared to most distances beyond our planet. The Moon sits close in cosmic terms. Mars, for example, can be about 56 million kilometers away at its closest approach. At its farthest, it can be more than 400 million kilometers away. That difference depends on where Earth and Mars sit in their orbits. Planets move, and distance between them changes over time. When we move even farther out, the numbers grow again. Jupiter is roughly 778 million kilometers from the Sun on average. Saturn is about 1.4 billion kilometers away. These distances are so large that astronomers often use a different unit to make things easier to compare. That unit is called the astronomical unit, or AU. 1 astronomical unit is the average distance between Earth and the Sun. It equals about 150 million kilometers. Using astronomical units helps shrink huge numbers into something more readable. In this system, Earth sits at 1 astronomical unit from the Sun. Mars orbits at about 1.5 astronomical units. Jupiter rests around 5 astronomical units. Pluto's average distance is close to 39 astronomical units. When distances are expressed this way, patterns become easier to see. But even astronomical unit eventually becomes too small when we think about stars. That is where the light year becomes useful. A light year measures how far light travels in 1 year. Since light moves at about 300,000 kilometers per second, it travels nearly 9.5 trillion kilometers in a year. The nearest star system, Alpha Centauri, lies about 4.37 light years away. That equals over 40 trillion kilometers. Even written out, that number remains hard to picture. It stretches beyond normal human experience. Another helpful way to understand distance is by thinking in terms of time. Light from the Sun takes about 8 minutes to reach Earth. Light from Jupiter can take more than 40 minutes. Light from Pluto can take over 5 hours. This delay matters because it shows how far apart objects truly are. If you sent a radio signal to Jupiter, you would wait nearly an hour for a reply when the planets are far apart. If you sent a message to Pluto, you could wait most of a day. As we move beyond Pluto, communication delays grow even longer. Signals from the Voyager spacecraft now take more than 20 hours to reach Earth. That means when engineers send a command, they wait almost a full day to see the result. Space adds patience to every interaction. Distance also depends on direction and path. Spacecraft rarely travel in straight lines. They follow curved paths shaped by gravity. Sometimes they swing around planets to gain speed, which changes both direction and travel time. A journey to Mars might not be the shortest physical line between 2 points. It might instead follow a carefully planned arc that uses less fuel. In space, the most efficient path is often not the shortest path. all of these ideas prepare us for a deeper question. When we talk about how far we can travel, are we measuring straight-line distance or orbital travel distance? Are we counting time spent accelerating or time spent coasting? These details shape what is possible. A spacecraft might reach a high speed briefly, but average speed over years matters more. What truly determines how far we can go is not peak speed. It is steady speed sustained over time. Once distance is understood in kilometers, astronomical units, and light years, something quiet happens. The solar system begins to feel structured rather than endless. The inner planets sit close together. The outer planets spread far apart. Beyond them, the sun's influence slowly fades. So before we talk about engines and propulsion, we need to hold this scale clearly in the mind. The moon is close. Mars is farther. Jupiter is far. Pluto is very far. The nearest star is unimaginably farther still. When these layers of distance settle into place, speed becomes meaningful. Only then can we compare our fastest spacecraft to the size of what lies ahead. And only then can we begin to see how far our reach might truly extend. Before we measure how far we can travel, we need to decide what tools we are allowed to use. The phrase "latest technology" can mean many different things. It could mean the fastest spacecraft ever built. It could mean rockets that are flying today. Or it could include engines that are still being tested. For this journey, we will focus on 3 levels of technology. First, we have systems that are fully operational and have already flown in space. Second, we have propulsion systems that are under active development and may fly within the next decade. Third, we have concepts that follow known physics but remain experimental. Let us begin with the spacecraft that have already set records. The Parker Solar Probe is currently the fastest human-made object ever built. At its closest approach to the Sun, it reaches about 191 kilometers per second. That equals roughly 690,000 kilometers per hour. That speed sounds almost impossible at first, but it comes from a special situation. The spacecraft falls deep into the Sun's gravity well, gaining speed as it approaches. It is not cruising outward at that speed forever. It is diving inward, then climbing back out again. Earlier missions also set impressive records. The Helios 2 spacecraft reached about 70 kilometers per second in the 1970s. Juno, during its approach to Jupiter, reached nearly 69 kilometers per second relative to Earth. These speeds show what gravity and careful planning can achieve. Voyager 1 and Voyager 2 offer another kind of record. They are not the fastest in a single moment. Instead, they show how far a spacecraft can travel after one strong push. Voyager 1 moves outward at about 17 kilometers per second relative to the Sun. It has been traveling for nearly 5 decades and is now beyond the outer boundary of the heliosphere. Chemical rockets remain the foundation of modern space travel. Vehicles like Falcon Heavy and NASA's Space Launch System provide enormous thrust at launch. They burn fuel quickly and deliver spacecraft into orbit or onto escape trajectories. After that initial push, however, most spacecraft rely on momentum rather than continuous thrust. Another important category is electric propulsion, such as ion engines. NASA's Dawn mission used ion propulsion to slowly build up speed over years. Ion engines provide very low thrust, but extremely high efficiency. They can continue accelerating for months at a time. Solar sails represent a different approach. Instead of carrying fuel, they use the gentle pressure of sunlight. The Japanese spacecraft Icaros demonstrated that light alone can change a spacecraft's speed. The acceleration is small, but it never runs out as long as sunlight is present. Now we move into technology that is not yet operational for deep space missions, but is being actively developed. Nuclear thermal propulsion is one example. In this system, a nuclear reactor heats a propellant like hydrogen, which then expands through a nozzle to create thrust. This approach could roughly double the efficiency of chemical rockets. Nuclear electric propulsion goes further. Instead of using nuclear heat directly for thrust, it uses nuclear power to generate electricity. That electricity then drives high-efficiency engines similar to ion thrusters. This system could provide steady acceleration over long durations, though it produces low thrust. Finally, there are concepts that remain experimental, but follow known physics. Breakthrough Starshot proposes using powerful ground-based lasers to push tiny sails to a fraction of light speed. The goal is about 20% of light speed for gram-scale probes. This idea requires enormous infrastructure and has not yet been built. For our question, we will focus mainly on technologies that are operational or realistically near-term. Chemical propulsion, gravity assists, and ion engines are proven. Nuclear thermal and nuclear electric systems are under development. Laser sails remain conceptual. By defining these categories clearly, we avoid mixing science fiction with engineering reality. We stay within the limits of known physics and existing programs. That keeps our question grounded. So when we ask how far we could travel using the latest technology, we are not imagining warp drives or wormholes. We are imagining rockets that burn real fuel, engines that push ions, reactors that heat hydrogen, and spacecraft that coast for decades through quiet space. Once the tools are clearly defined, we can begin comparing their speeds. And once we compare their speeds to the size of the solar system, the boundary of our reach begins to sharpen into view. The Parker Solar Probe holds a record that feels almost impossible at first. At its closest approach to the Sun, it reaches about 191 kilometers per second. That equals nearly 690,000 kilometers per hour. It is the fastest human-made object ever built. To understand that speed, it helps to compare it to something familiar. At 191 kilometers per second, a spacecraft could circle Earth in just over 3 minutes. It could travel from New York to Los Angeles in around 20 seconds. It could cross the entire width of Europe in less than half a minute. Those comparisons feel dramatic, yet they remain grounded in real numbers. The speed is not imagined. It has already been achieved. The Parker Solar Probe reached that velocity during its close passes around the Sun. But the way it reached that speed matters. The spacecraft did not fire a massive engine for hours. It used gravity. More specifically, it used repeated flybys of Venus to reshape its orbit and fall deeper toward the Sun. Each flyby around Venus acted like a careful adjustment. It reduced the spacecraft's orbital energy relative to the Sun. Over time, these adjustments allowed Parker to drop closer and closer to the solar surface. As it fell inward, gravity pulled it faster and faster. This is an important detail. The spacecraft becomes fastest when it is closest to the Sun. It is not accelerating outward into deep space at 191 kilometers per second. It is diving inward, gaining speed as it descends into a strong gravitational field. At its closest approach, Parker travels through the Sun's outer atmosphere, known as the corona. Temperatures there can reach millions of degrees Celsius. To survive, the spacecraft carries a carbon composite heat shield nearly 12 centimeters thick. The heat shield protects delicate instruments from extreme radiation and heat. Without it, the spacecraft would not last long near the Sun. The mission design balances speed, protection, and scientific goals very carefully. After each close pass, Parker climbs back outward along its elliptical orbit. As it moves away from the Sun, gravity slows it down again. Its speed decreases as distance increases. This rise and fall in speed follows the basic rules of orbital motion. This pattern reveals something subtle about space travel. Peak speed is not the same as sustained cruise speed. A spacecraft can briefly reach extraordinary velocity, yet average speed over long distances may be much lower. If Parker were pointed straight outward and allowed to escape the Sun's gravity entirely, its long-term outward speed would not remain at 191 kilometers per second. It would settle into a lower cruise velocity determined by its total energy. This distinction matters for our larger question. When we ask how far we can travel, we care about how fast we can move steadily over decades. A brief moment of extreme speed near the Sun does not automatically translate into rapid travel between stars. Even so, Parker's record is meaningful. It shows that gravity itself can act as an accelerator. It shows that careful mission design can push hardware to remarkable limits. It demonstrates that we can build machines that survive environments once thought unreachable. Yet, when we compare Parker's speed to the speed of light, the gap becomes clear. Light moves at about 300,000 kilometers per second. Parker's peak speed is about 0.064% of light speed. That fraction is small. At 0.064% of light speed, the nearest star remains thousands of years away. Even at the fastest speed ever achieved by human technology, interstellar travel remains far beyond a single lifetime. This contrast does not diminish the achievement. It simply frames it within cosmic scale. The Parker Solar Probe represents the upper edge of what current propulsion and gravity can accomplish. It is our benchmark for real demonstrated speed. As we move forward, we will compare this record to other spacecraft and propulsion systems. We will examine steady outward speeds rather than peak dive speeds. And we will begin asking how long it would take to cross the solar system at different velocities. The fastest object we have ever built shows both our capability and our limits. It reveals how powerful gravity can be, and it quietly reminds us that space remains vast beyond measure. Before the Parker Solar Probe set its record, another spacecraft held the title of fastest object ever built. In the 1970s, Helios 2 reached a speed of about 70 kilometers per second. That equals roughly 252,000 kilometers per hour. At the time, that number felt almost unbelievable. Helios 2 achieved its record in a way that now feels familiar. It traveled in a highly elliptical orbit around the Sun. At its closest approach, gravity pulled it inward and increased its speed dramatically. Just like Parker decades later, Helios used the Sun itself as part of its acceleration. This idea may seem simple, yet it is powerful. When an object falls toward a massive body like the Sun, it gains speed. When it climbs back outward, it slows down again. The change in speed follows the basic rules of orbital mechanics. Helios did not carry a massive engine that fired continuously. It relied on its launch energy and the shape of its orbit. Once placed on the correct path, gravity did the rest. The Sun became both destination and accelerator. The same principle appears in many space missions. Spacecraft often use gravity assists to change direction and speed. A gravity assist happens when a spacecraft swings close to a planet. As it passes by, it borrows a small amount of the planet's orbital energy. The effect is subtle but meaningful. The planet continues its orbit almost unchanged. The spacecraft, however, leaves the encounter moving faster relative to the Sun. This method allows engineers to increase speed without carrying extra fuel. Voyager 1 and Voyager 2 used gravity assists in a remarkable sequence. In the late 1970s, the outer planets aligned in a rare formation. This alignment allowed the Voyagers to fly past Jupiter and Saturn, gaining speed and changing direction along the way. Each flyby acted like a carefully timed push. Jupiter's gravity added significant energy to the spacecraft. Saturn adjusted their paths even further. Voyager 2 later visited Uranus and Neptune as well, using each encounter to shape its journey. These gravity assists did not create record-breaking peak speeds like Parker's dive near the Sun. Instead, they created steady outward motion. Voyager 1 now moves away from the Sun at about 17 kilometers per second. That may sound modest compared to 191 kilometers per second. But the key difference lies in direction and endurance. Voyager is not diving inward and climbing back out. It is moving steadily outward, year after year. It has been traveling for nearly 5 decades, covering billions of kilometers. This comparison reveals something important about speed in space. The fastest moment is not always the most useful measure. A brief high velocity during a close approach may look impressive. Long-term outward speed determines how far you will actually go. New Horizons offers another example of this balance. When it launched in 2006, it became the fastest spacecraft ever to leave Earth. Its launch speed was about 16 kilometers per second relative to Earth. Later, a gravity assist from Jupiter added several kilometers per second to its outward motion. After that assist, New Horizons reached speeds above 23 kilometers per second. That steady outward pace carried it to Pluto in just under 10 years. The mission showed how combining launch energy and gravity assists can shorten travel time across the solar system. Even so, these speeds remain small compared to light. At 17 or 23 kilometers per second, reaching another star would take tens of thousands of years. The outer planets are reachable within years or decades. Interstellar space remains far beyond that scale. Gravity assists feel almost like a clever shortcut. They allow spacecraft to gain speed without carrying extra fuel. They turn planetary motion into a resource. Yet they are limited by planetary positions and orbital mechanics. You cannot swing around a planet that is not in the right place. You cannot gain unlimited energy from a single flyby. Each maneuver must be carefully planned years in advance. These earlier speed records and orbital tricks show how creative mission design can stretch our reach. They reveal that we have learned to use gravity itself as part of our toolkit, and they quietly prepare us for the next step, which is comparing steady cruise speeds to the vast distances that still lie ahead. Some spacecraft become fast, not because they burn fuel for a long time, but because they fall towards something massive. When NASA's Juno spacecraft approached Jupiter in 2016, it reached a speed of about 57 kilometers per second relative to Jupiter. That equals more than 200,000 kilometers per hour. For a brief period, Juno was moving faster than almost any spacecraft in history. That speed came from a combination of launch energy and gravity. Juno was launched in 2011 aboard an Atlas V rocket. After leaving Earth, it did not head straight to Jupiter. Instead, it performed a flyby of Earth in 2013, using our planet's gravity to gain additional speed. This Earth flyby acted like a carefully timed boost. By passing behind Earth relative to its orbit around the Sun, Juno borrowed a small amount of Earth's orbital momentum. That added velocity helped it reach Jupiter using less fuel. When Juno finally approached Jupiter, the giant planet's gravity pulled it inward. Jupiter is more than twice as massive as all the other planets combined. Its gravitational field is strong and deep. As Juno fell toward it, the spacecraft accelerated rapidly. This is a pattern we have seen before. Falling toward a massive body increases speed. Climbing away decreases speed. The closer the approach, the greater the velocity change. Jupiter's gravity well is second only to the Sun's in our solar system. At its closest approach, Juno's speed relative to Jupiter peaked at roughly 57 kilometers per second. Relative to the Sun, the speed was slightly different. These differences depend on the reference frame being used. Speed in space always depends on what you are measuring against. However, Juno did not remain at that speed. In order to enter orbit around Jupiter, the spacecraft had to slow down. It fired its main engine for about 35 minutes in what was called the Jupiter Orbit Insertion Burn. This burn reduced its velocity just enough for Jupiter's gravity to capture it into orbit. This detail highlights an important idea. The fastest moment of a mission is often not the goal. Juno was designed to study Jupiter closely for years. To do that, it needed to orbit the planet, not fly past it. That required braking, not accelerating. So in one sense, Juno became incredibly fast. In another sense, it had to give up that speed in order to stay. The mission shows how speed and destination are linked. Sometimes moving slower allows you to stay longer and gather more information. Juno's sprint toward Jupiter also demonstrates the power of launch energy. The initial rocket provided a strong push. The Earth flyby added more speed without using additional propellant. Gravity did much of the work once Juno reached the outer solar system. This layered approach to acceleration is common in deep space missions. Rockets provide the first push. Gravity assists reshape the path. Large planets can either speed you up or slow you down, depending on the trajectory. Yet even at 57 kilometers per second, Juno's speed remains small compared to light. Light travels at about 300,000 kilometers per second. Juno's peak speed was less than 0.02% of light speed. If Juno had continued outward instead of entering orbit, it would still take tens of thousands of years to reach the nearest star. The difference between planetary travel and interstellar travel remains vast. What Juno shows us is not a pathway to the stars, but a clear example of how planetary gravity shapes our missions. It shows that speed is often temporary. It shows that capturing into orbit requires slowing down. And it reminds us that space travel is often about balance rather than maximum velocity. The lesson from Juno is subtle but important. A spacecraft can move incredibly fast and still remain within the boundaries of the solar system. The outer planets are reachable with careful planning and patience. The stars remain far beyond that reach. As we move forward, we will compare these arrival speeds with steady outward speeds. We will begin to ask which velocities matter most for long-distance travel. And we will slowly shift from brief sprints near planets to the quiet, steady motion that defines the edge of our reach. If we want to understand how far we can truly travel, we need to look at a spacecraft that has already been traveling for decades. Voyager 1 launched in 1977. Voyager 2 launched just weeks later. They were not designed to break speed records. They were designed to explore the outer planets and keep going. At launch, both spacecraft received a powerful push from chemical rockets. After leaving Earth, they used gravity assists from the giant planets to gain additional speed. Jupiter provided the largest boost. Saturn reshaped their paths. Voyager 2 continued on to Uranus and Neptune, using each encounter to adjust its course. Today, Voyager 1 travels outward from the Sun at about 17 kilometers per second. Voyager 2 moves slightly slower, at about 15 kilometers per second. These speeds may sound modest compared to Parker's solar probe or Juno's peak approach speeds. Yet they represent something different. Voyager's speed is steady and outward. It is not diving inward toward the Sun. It is not slowing down to enter orbit around a planet. It is simply coasting away from the solar system, year after year. This steady outward motion makes Voyager the best real-world example of long-distance travel using current technology. The spacecraft no longer fire engines for propulsion. They rely on momentum gained during their early gravity assists. In space, once you are moving, you keep moving unless acted upon by another force. Voyager 1 crossed the boundary of the heliosphere in 2012. The heliosphere is the bubble of charged particles flowing outward from the Sun. Crossing that boundary means Voyager entered interstellar space, where the influence of the Sun's solar wind weakens and the interstellar medium begins. Even so, Voyager is still far from the nearest star. After nearly 50 years of travel, Voyager 1 is about 160 astronomical units from the Sun. 1 astronomical unit equals the average distance between Earth and the Sun, about 150 million kilometers. That means Voyager has traveled roughly 24 billion kilometers. That distance feels enormous on human scales. It is far beyond Pluto's orbit. It is far beyond the main Kuiper Belt. Yet it remains only a tiny fraction of the distance to Alpha Centauri, which lies more than 4 light-years away. At 17 kilometers per second, it would take Voyager about 75,000 years to reach the nearest star system. That timescale stretches beyond recorded human history. It reminds us that crossing into interstellar space is not the same as reaching another star. Voyager also shows how spacecraft can operate for extraordinary lengths of time. Both spacecraft are powered by radioisotope thermoelectric generators, or RTGs. These devices convert heat from the decay of plutonium into electricity. They do not rely on sunlight, which becomes weak in the outer solar system. Over time, the power output of the RTGs slowly decreases. Engineers have turned off instruments one by one to conserve energy. Even so, the spacecraft continue to send data back to Earth. Signals from Voyager now take more than 20 hours to reach us. Communication delay becomes part of the mission at these distances. Commands must be planned carefully. There is no real-time control. Space feels slower, not because the spacecraft moves slowly, but because light itself takes time to travel. Voyager gives us a grounded baseline. It shows what is possible when a spacecraft receives a strong initial push and then coasts for decades. It shows that leaving the solar system is achievable with existing technology. At the same time, it shows the limits of that technology. Even after half a century, Voyager remains closer to the Sun than the Sun is to any other star. The distance between stars remains vast beyond comparison. This steady outward journey provides a realistic measure for our question. If we rely on gravity assists and chemical rockets alone, our cruise speeds fall within the range of 15 to 20 kilometers per second. That speed allows us to explore the outer planets and cross the heliosphere within decades. Reaching another star at that pace would require tens of thousands of years. Voyager demonstrates both our capability and our boundary. It shows how far one powerful launch and a few gravity assists can carry a spacecraft. And it quietly reminds us that even decades of travel may still leave us at the edge of a much larger ocean. Sometimes, the fastest part of a mission happens right at the beginning. When NASA launched the New Horizons spacecraft in January 2006, it became the fastest object ever to leave Earth. At launch, it was moving at about 16.3 kilometers per second relative to Earth. That equals nearly 59,000 kilometers per hour. That speed did not come from long-term engine burns in deep space. It came from a powerful chemical rocket at liftoff. The Atlas V rocket, combined with an additional solid rocket booster stage, gave New Horizons a tremendous push. Most of the energy needed for its journey was delivered in those first minutes after launch. Once New Horizons escaped Earth's gravity, it entered orbit around the Sun. From that point forward, it was mostly coasting. It did not carry massive engines designed to keep accelerating. Like many deep space missions, it relied on initial momentum and careful planning. In 2007, New Horizons performed a gravity assist at Jupiter. This maneuver added about 4 kilometers per second to its heliocentric velocity. That may sound small compared to the numbers we have seen near the Sun, but over long distances, even a few kilometers per second makes a meaningful difference. The Jupiter flyby shortened the spacecraft's travel time to Pluto by several years. Without that assist, the journey would have taken longer. By borrowing a bit of Jupiter's orbital motion, New Horizons gained speed and without burning extra fuel. After the gravity assist, New Horizons traveled outward at about 23 kilometers per second relative to the Sun. That steady outward pace carried it across the solar system. In July 2015, just under 10 years after launch, it flew past Pluto. That timeline is important. Pluto sits about 39 astronomical units from the Sun on average. Reaching it in less than a decade required both strong launch energy and planetary assistance. It shows what is possible when speed and alignment work together. However, New Horizons did not continue accelerating after Jupiter. Its engines are small and used mainly for trajectory corrections. Most of its outward motion comes from the momentum gained early in the mission. Like Voyager, it is now coasting deeper into the Kuiper Belt. This pattern appears again and again in space exploration. Rockets provide a brief but powerful push. Gravity assists adjust and add to that motion. After that, spacecraft drift through space at nearly constant speed. New Horizons demonstrates the upper limit of what launch energy can accomplish with chemical propulsion. It left Earth faster than any spacecraft before it. Yet even at 23 kilometers per second, reaching another star would take tens of thousands of years. To understand that scale, consider this simple comparison. At 23 kilometers per second, a spacecraft travels about 725 million kilometers per year. That sounds immense. But 1 light year equals about 9.5 trillion kilometers. The gap between those two numbers is vast. New Horizons shows that we can cross the outer solar system within a human lifetime. It shows that Pluto and the Kuiper Belt are reachable with today's technology. It also shows that leaving the heliosphere entirely, as Voyager has done, takes decades. The mission reminds us that speed in space often comes in layers. Launch energy provides the first layer. Planetary gravity provides the second. After that, motion becomes steady and patient. New Horizons continues its journey today. It has already flown past a small Kuiper Belt object named Arakoth. It remains operational, sending back data from the distant edge of the solar system. This spacecraft serves as another real-world benchmark. If we rely on chemical rockets and gravity assists, outward cruise speeds of 20 to 25 kilometers per second are achievable. That speed allows exploration of distant planets and icy worlds within decades. Yet it also reinforces a quiet truth. Even our fastest launches, combined with planetary boosts, do not bring the stars within reach of a single lifetime. They bring the solar system within reach. Beyond that, the distances begin to expand again. New Horizons teaches us that strong beginnings matter. A powerful launch can shorten journeys by years. A well-timed flyby can reshape destiny. But once momentum is set, patience becomes the defining feature of travel. As we move forward, we will compare these cruise speeds to different travel scenarios. We will begin calculating how far 20, 50, or 150 kilometers per second can carry us over decades. And we will slowly translate momentum into distance across the wide architecture of our solar system. When most people picture a rocket, they imagine fire and smoke rising into the sky. Chemical rockets are loud, powerful, and dramatic. They produce enormous thrust for a short period of time. Nearly every spacecraft we have discussed so far began its journey this way. Chemical rockets work by burning fuel and oxidizer together. The reaction creates hot gas that expands rapidly. That gas is forced out of a nozzle at high speed. As it shoots backward, the rocket moves forward. This method produces very strong thrust. It allows spacecraft to lift off from Earth's surface. It allows them to escape Earth's gravity. It allows them to reach orbit or head into deep space. But chemical propulsion has limits. The fuel burns quickly. Once it is gone, the rocket cannot continue accelerating. Most of the spacecraft's speed is gained during the first few minutes of launch. To leave Earth entirely, a spacecraft must reach escape velocity. Escape velocity from Earth's surface is about 11.2 kilometers per second. That means if you reach that speed and keep moving outward, Earth's gravity will not pull you back. However, escape velocity does not mean you are moving at 11.2 kilometers per second forever. It simply means you have enough energy to break free. Additional speed can be added by further engine burns or gravity assists. Rockets like Falcon Heavy and NASA's Space Launch System are designed to provide large amounts of thrust. Falcon Heavy can deliver heavy payloads into orbit or toward the Moon and Mars. The Space Launch System is built to send crewed missions beyond low Earth orbit. These rockets are extremely powerful, yet their job lasts only minutes. After the stages separate and the fuel is spent, the spacecraft continues on its path using the momentum it already has. This is an important shift in thinking. Rockets do not push spacecraft for years. They push them briefly. Deep space travel is mostly coasting. The reason for this lies in the rocket equation, which we will explore more deeply later. To carry more fuel, you must add more mass. To lift more mass, you need more fuel. This cycle grows quickly and becomes difficult to sustain. Because of this, chemical propulsion cannot accelerate a spacecraft continuously for long periods. It is ideal for strong initial acceleration. It is less suitable for sustained deep space thrust. Another key detail is efficiency. Chemical rockets convert chemical energy into motion. Their exhaust velocity is limited by the chemistry of the fuel. This sets a cap on how much speed they can realistically provide. Even the most advanced chemical rockets today operate within similar physical limits as rockets built decades ago. Materials improve, engineering improves, but the underlying chemistry stays within known boundaries. This does not mean chemical rockets are weak. They are essential. Without them, we would not reach orbit at all. They provide the foundation for all other space missions. However, when we ask how far we can travel using the latest technology, chemical rockets mostly determine how fast we leave Earth. They do not determine how fast we travel across the entire solar system. Once in deep space, spacecraft move quietly. They follow curved paths shaped by gravity. They adjust with small thrusters, but they are no longer accelerating the way they were at launch. If a spacecraft leaves Earth at about 16 kilometers per second relative to Earth, that speed becomes its baseline. Additional boosts from planetary flybys can raise it further, but chemical engines rarely operate continuously for years to keep adding speed. So chemical rockets are like a powerful jump at the beginning of a journey. They determine the initial direction and energy. After that jump, gravity and momentum carry the spacecraft onward. This pattern shapes the boundary of our reach. With chemical propulsion alone, steady cruise speeds in deep space tend to fall between 15 and 25 kilometers per second. That is enough to explore the outer planets over decades. It is not enough to cross the distance to another star within a human lifetime. The energy required to accelerate a large spacecraft to even a small fraction of light speed far exceeds what chemical reactions can provide. Chemical rockets show us both strength and limitation. They lift us off the ground. They send us outward. And then they step aside, leaving us to drift through the quiet expanse that lies beyond Earth's gravity well. Not every engine in space is loud and fiery. Some engines are quiet and almost invisible. Ion propulsion systems produce only a faint glow of charged particles. They do not roar like chemical rockets. They whisper. An ion engine works by taking a gas, often xenon, and stripping electrons from its atoms. This creates positively charged ions. Electric fields then accelerate those ions out of the engine at very high speeds. As the ions shoot backward, the spacecraft moves forward. The thrust produced by an ion engine is extremely small. It is often compared to the weight of a sheet of paper resting on your hand. You would never feel it pushing in a dramatic way. Yet in space, where there is no air resistance, even a tiny force applied for a long time can build meaningful speed. NASA's Dawn spacecraft is one of the best examples of this technology. Dawn used ion propulsion to travel to the asteroid belt. Over the course of its mission, Dawn changed its velocity by more than 10 kilometers per second using its ion engines. That change did not happen quickly. It happened slowly, over months and years. This is the key difference between chemical rockets and ion engines. Chemical rockets provide large thrust for a short time. Ion engines provide very small thrust for a very long time. Over extended periods, that steady push can add up. Ion propulsion is much more fuel efficient than chemical propulsion. The exhaust velocity of ions is far higher than the exhaust velocity of hot chemical gases. This means each kilogram of propellant provides more change in velocity. Engineers describe this efficiency using a term called specific impulse. Ion engines have much higher specific impulse than chemical rockets. However, ion engines require electricity. Dawn used large solar panels to generate the power needed to accelerate its ions. Near Earth, sunlight is strong enough to support this. As spacecraft travel farther from the sun, sunlight becomes weaker. Solar panels must become larger to collect enough energy. For missions beyond Jupiter, solar power becomes limited. This is one reason Voyager and other outer solar system missions use radioisotope power sources instead of solar panels. Ion engines could still operate with nuclear-generated electricity, but that adds complexity and mass. Another limitation of ion engines is thrust level. Because the force is small, ion engines are not useful for launching from Earth. They cannot lift a spacecraft off the ground. They are best used once a spacecraft is already in space and free from atmospheric drag. Ion propulsion is ideal for robotic missions that do not require quick travel times. It allows spacecraft to spiral gradually outward from one orbit to another. It allows fine adjustments and long-term acceleration. It makes efficient use of limited propellant. For crewed missions, the situation becomes more complex. humans require life support systems, radiation shielding, and supplies. These add mass. Accelerating a heavy spacecraft using low thrust takes time. Even with continuous thrust for years, the final speeds remain modest compared to the speed of light. Still, ion propulsion changes the conversation. It allows steady acceleration rather than a single initial push. If operated long enough, an ion-powered spacecraft could reach cruise speeds higher than those achieved by chemical rockets alone. For example, if an ion engine produced continuous acceleration for several years, it could add several kilometers per second to a spacecraft's speed. That might shorten travel times to Mars or the asteroid belt. It could improve missions to the outer planets. Yet even here, scale remains humbling. Suppose a spacecraft achieved a steady outward speed of 50 kilometers per second using advanced electric propulsion. That would be more than twice Voyager's speed. At that pace, reaching Alpha Centauri would still take more than 25,000 years. Ion engines teach us patience. They show that small forces applied steadily can produce meaningful change. They reveal that efficiency matters as much as raw thrust. They also reveal that even efficient propulsion operates within firm physical boundaries. Electricity must come from somewhere. Power systems add weight. Acceleration over years still falls far short of interstellar speeds. Ion propulsion represents a thoughtful evolution in our technology. It does not replace chemical rockets. It complements them. Chemical rockets provide the initial energy to escape Earth. Ion engines refine and extend the journey. Together, they stretch our reach deeper into the solar system. They allow more precise navigation and longer missions. But when measured against the immense distances between stars, even years of gentle acceleration remain a small step within a very large expanse. There is another way to move through space without burning fuel. Instead of pushing against hot gas, a spacecraft can push against light. Sunlight carries momentum, even though it feels weightless to us. When light strikes a reflective surface, it transfers a tiny amount of force. This idea may sound subtle, but it is real and measurable. Photons, the particles of light, do not have mass in the usual sense, yet they carry energy and momentum. When billions of photons strike a surface each second, they can create pressure. This pressure is very small. At Earth's distance from the Sun, sunlight produces a force of about 9 micronewtons per square meter on a perfectly reflective surface. That is far less than the weight of a feather. But in space, even this gentle push never stops. The Japanese spacecraft Icaros demonstrated solar sailing in 2010. It deployed a thin, reflective sail about 14 meters across. Sunlight striking the sail produced measurable acceleration. Over time, that small push changed the spacecraft's speed and trajectory. Unlike chemical rockets, solar sails do not carry propellant. They rely entirely on sunlight. As long as the sail remains intact and exposed to light, acceleration continues. There is no fuel tank to empty. This feature makes solar sails attractive for long missions. A spacecraft could, in theory, keep gaining speed slowly for months or years. The total change in velocity might eventually exceed what chemical propulsion alone could provide. However, the acceleration remains extremely small. Solar sail spacecraft must be very light. Large, thin sails are required to capture enough sunlight to produce useful thrust. Increasing the payload mass reduces acceleration significantly. For this reason, solar sails have so far been tested mainly with small spacecraft. Carrying heavy instruments or human crews would require enormous sail structures. Building and deploying such structures presents engineering challenges. Another factor is distance from the sun. Sunlight becomes weaker as you move farther outward. At twice Earth's distance, the intensity of sunlight drops to 1/4. That means acceleration decreases rapidly in the outer solar system. Some mission designs propose sending a solar sail inward first, closer to the sun. There, sunlight is much stronger. The sail could gain speed before heading outward again. This approach mirrors how gravity assists are used, but with light instead of planetary motion. Even so, the speeds achieved remain modest compared to light speed. Solar sails might allow spacecraft to reach tens of kilometers per second over long periods. They could help reduce travel times to outer planets or distant asteroids. For interstellar travel, sunlight alone becomes insufficient. Beyond the heliosphere, the sun's light fades into the background of the galaxy. Acceleration would slow to nearly nothing. This limitation has led to experimental concepts such as laser sails. In those proposals, powerful lasers based on Earth would push a tiny sail to a much higher speed. The breakthrough Starshot concept aims to accelerate gram-scale probes to about 20% of light speed. However, this idea remains theoretical and would require enormous infrastructure. It is not operational technology today. Solar sailing using natural sunlight is proven. Laser propulsion remains conceptual. Solar sails offer a different way to think about motion. They show that propulsion does not always require burning fuel. They reveal that light itself can act as a steady driver. They also remind us that the size of space matters. Even continuous acceleration from sunlight leads to gradual increases in speed. Over years, that change adds up. Over interstellar distances, it remains small. Solar sailing expands our toolkit. It provides a fuel-free method of propulsion within the inner solar system. It may enable long-duration missions with low mass. Yet when we place solar sails beside the vast distances between stars, the boundary remains clear. Light can push gently and endlessly, but the universe stretches far beyond what that gentle push can cross in a single lifetime. Speed can mean different things depending on where you measure it. A spacecraft can be moving very quickly relative to Earth, yet differently relative to the Sun. It can have a brief moment of extreme velocity, yet travel much more slowly on average. These differences shape how far we can actually go. When a rocket launches from Earth, its first goal is to escape Earth's gravity. Escape velocity from Earth is about 11.2 kilometers per second. That number is measured relative to Earth. It describes how fast the spacecraft must move to avoid falling back down. Once the spacecraft leaves Earth's influence, it begins orbiting the Sun instead. Now its speed is measured relative to the Sun. Earth itself moves around the Sun at about 30 kilometers per second. So a spacecraft leaving Earth already carries some of that orbital motion. This is why speed in space is always relative. If you measure a spacecraft's velocity relative to Earth, you may get one number. If you measure it relative to the Sun, you may get another. Both are correct. They simply depend on your frame of reference. The same idea appears when we talk about record speeds. The Parker Solar Probe reaches about 191 kilometers per second at its closest approach to the Sun. That number sounds extraordinary, and it is. But it occurs at a specific point in its orbit. That peak happens during a deep dive near the Sun. As Parker moves away from the Sun, its speed decreases. Its average speed over its full orbit is much lower than its peak speed. This difference between fastest moment and average travel speed is essential. If a spacecraft reaches 191 kilometers per second for a short time, that does not mean it travels outward at that speed forever. For long-distance travel, average speed over years is what determines how far you go. Curved paths also change how we think about speed. Spacecraft rarely travel in straight lines. They follow elliptical or hyperbolic orbits shaped by gravity. As they swing around planets, their direction changes. Their speed relative to one object may increase, while relative to another, it changes differently. Gravity assists add another layer to this story. When a spacecraft swings behind a planet relative to the Sun, it can gain speed. That gain depends on the planet's own motion around the Sun. The spacecraft borrows a small amount of that orbital energy. However, gravity assists do not create unlimited acceleration. They depend on planetary alignment. They provide a boost at a specific moment. After the encounter, the spacecraft settles into a new steady trajectory. All of this leads to a simple idea. Distance traveled equals average speed multiplied by time. If a spacecraft averages 20 kilometers per second over a year, it will travel about 630 million kilometers in that year. If it averages 50 kilometers per second, it will travel more than twice that distance. This rule is calm and reliable. It does not depend on dramatic peaks. It does not depend on momentary bursts of acceleration. It depends on steady motion over long periods. When we compare spacecraft for deep space travel, we should focus on their sustained cruise speeds. Voyager travels outward at about 17 kilometers per second. New Horizons travels at about 23 kilometers per second. These are not their highest speeds ever achieved. They are their long-term outward velocities. These steady numbers are the ones that matter for crossing the solar system. They determine how long it takes to reach the Kuiper Belt. They determine how many decades it takes to cross the heliosphere. Peak speeds may sound impressive, but they do not define the journey. A spacecraft can briefly move very fast and still remain within the solar system for decades. Average speed, applied over years, sets the true boundary of distance. So when we ask how far we could travel using the latest technology, we should not focus only on the fastest moment ever recorded. We should ask what steady speed we can maintain. We should ask how long that speed can be sustained. Because in space, motion is patient. The universe does not measure travel in seconds. It measures travel in years. And the calm way to measure distance is to multiply a steady speed by the quiet passage of time. Now that we understand how speed can vary depending on how it is measured, we need a few simple numbers to guide the rest of our journey. Instead of jumping between many different spacecraft speeds, we will choose a small set of steady cruise speeds. These will help us compare distances clearly and calmly. The first benchmark will be 20 kilometers per second. This number is close to the outward cruise speeds of Voyager and New Horizons. It represents what is realistically achievable today using chemical rockets and gravity assists. At 20 kilometers per second, a spacecraft travels 72,000 kilometers every hour. In one day, it would travel about 1.7 million kilometers. Over a full year, it would cover roughly 630 million kilometers. Our second benchmark will be 50 kilometers per second. This speed is faster than Voyager's steady cruise, and it represents what might be possible with advanced electric propulsion or carefully optimized gravity assists. It is more ambitious than today's typical missions, but still within the realm of near-term physics. At 50 kilometers per second, a spacecraft travels 180,000 kilometers per hour. In one day, it would cover more than 4.3 million kilometers. In 1 year, it would travel about 1.6 billion kilometers. The third benchmark will be 150 kilometers per second. This is close to the peak speed reached by the Parker Solar Probe during its solar dives. It is far beyond normal cruise speeds, but it shows us what extremely high velocities look like within our solar system. At 150 kilometers per second, a spacecraft travels 540,000 kilometers per hour. In one day, it would move about 13 million kilometers. In a year, it would travel roughly 4.7 billion kilometers. These first three benchmarks remain within the range of kilometers per second. They help us understand what is achievable with existing propulsion methods or realistic extensions of them. Now we add two light fraction benchmarks to stretch our imagination further. The first is 0.1% of the speed of light. Light travels at about 300,000 kilometers per second. 1/10 of 1% of that speed equals about 300 kilometers per second. At 300 kilometers per second, a spacecraft would travel more than 1 million kilometers every hour. In a single day, it would cover about 26 million kilometers. Over 1 year, it would travel nearly 9.5 billion kilometers. The final benchmark will be 1% of the speed of light. 1% of light speed equals about 3,000 kilometers per second. This is far beyond what current propulsion systems can achieve. It remains a theoretical upper boundary for advanced future systems. At 3,000 kilometers per second, a spacecraft would travel more than 10 million kilometers every hour. In one day, it would move about 260 million kilometers. In 1 year, it would travel roughly 95 billion kilometers. Placing these five speeds side by side gives us a clear ladder. At 20 kilometers per second, we move steadily through the outer solar system over decades. At 50 kilometers per second, travel times shorten noticeably. At 150 kilometers per second, distances shrink further within the solar system. At 0.1% of light speed, interstellar travel begins to shift from tens of thousands of years to thousands of years. At 1% of light speed, the nearest star could be reached in a few hundred years, rather than tens of thousands. These numbers are not promises. They are tools for comparison. They allow us to place familiar destinations along a timeline. They help us translate abstract distances into years of travel. For the rest of this video, we will imagine spacecraft traveling at these steady cruise speeds. We will not assume sudden bursts or changing velocities. We will simply multiply steady speed by time and see where that carries us. This method keeps the picture clear. It avoids confusion between peak speeds and sustained speeds. It focuses on what matters most for distance: the quiet accumulation of motion over years. With a few speeds chosen, the solar system becomes easier to map. We can now ask how long it would take to reach the Moon at each speed. We can calculate travel times to Mars, Jupiter, and Pluto. And once we extend those same speeds across decades, we can see how far a human lifetime might carry us. With a few steady benchmarks in place, the map of our reach begins to feel readable and calm. Now that we have chosen our benchmark speeds, we can begin moving outward. Instead of thinking only in kilometers, we can think in years and days. Travel time often feels more real than raw distance. So let us walk through the solar system, one destination at a time. We begin with the Moon. The Moon sits about 384,000 kilometers from Earth. At 20 kilometers per second, a spacecraft would reach the Moon in a little over 5 hours. At 50 kilometers per second, the trip would take just over 2 hours. At 150 kilometers per second, it would take about 43 minutes. At 0.1% of light speed, which equals 300 kilometers per second, the Moon would be reached in about 21 minutes. At 1% of light speed, or 3,000 kilometers per second, the journey would take a little over 2 minutes. The Moon feels close in cosmic terms. Even at our slowest benchmark, it lies within hours. That is why human missions to the Moon were possible using 1960s technology. Next, we move to Mars. Mars does not stay at a fixed distance from Earth. At its closest, it can be about 56 million kilometers away. At its farthest, it can be more than 400 million kilometers away. If Mars were at its closest approach, and a spacecraft traveled at 20 kilometers per second, the journey would take about 32 days. At 50 kilometers per second, it would take about 13 days. At 150 kilometers per second, it would take about 4 days. At 0.1% of light speed, the closest Mars approach would take about 2 days. At 1% of light speed, it would take just under 5 hours. When Mars is farthest away, travel times stretch. At 20 kilometers per second, the trip could take about 231 days. At 50 kilometers per second, about 93 days. At 150 kilometers per second, about 31 days. These differences show how orbital positions shape travel time. Mars can feel nearby or distant depending on where the planets are. Now we move farther outward to Jupiter. Jupiter orbits about 5 astronomical units from the Sun, which equals roughly 778 million kilometers. From Earth, the distance varies, but we can use about 628 million kilometers as a typical closest approach. At 20 kilometers per second, reaching Jupiter at that distance would take about 1 year. At 50 kilometers per second, it would take about 5 months. At 150 kilometers per second, about 2 months. At 0.1% of light speed, Jupiter could be reached in about 24 days. At 1% of light speed, in just over 2 days. Beyond Jupiter lies Pluto, at an average distance of about 39 astronomical units from the Sun. From Earth, Pluto can be roughly 5.9 billion kilometers away at its closest. At 20 kilometers per second, reaching Pluto would take about 9 years. At 50 kilometers per second, about 3.7 years. At 150 kilometers per second, about 1.2 years. At 0.1% of light speed, the journey would take about 7 months. At 1% of light speed, about 22 days. These numbers reveal something steady and clear. Within the solar system, even moderate increases in speed dramatically shorten travel times. The difference between 20 and 50 kilometers per second can cut years down to months. However, even at 150 kilometers per second, crossing to Pluto still requires more than a year. And Pluto sits well within the Sun's gravitational reach. The inner solar system lies within days or weeks at higher speeds. The outer solar system stretches into years. Each outward step adds not just distance, but patience. These familiar destinations begin to feel like time zones rather than points on a map. The Moon sits in hours, Mars in days or months, Jupiter in months, Pluto in years. As we move farther outward beyond Pluto, travel times begin to stretch into decades. And once we begin speaking in decades, a human lifetime quietly enters the conversation. The solar system is large, yet it is still measurable. With steady cruise speeds, we can map its distances into years and months. The farther we walk outward, the more time becomes the true measure of distance. And beyond the edge of this planetary map, time begins to stretch even more dramatically. Distance feels different when it is measured against a human life. A number like 5 billion kilometers sounds abstract, but 50 years feels personal. So now we place our benchmark speeds inside a lifetime. Let us imagine someone launches at age 30. They live to age 80. That gives them about 50 years of travel time. We will assume steady cruise speeds, not constant acceleration. We will simply multiply speed by time and see where it leads. 50 years contains about 1.6 billion seconds. That number may feel large, but it is simply the total time available for the journey. If a spacecraft travels at 20 kilometers per second for 50 years, it would cover about 32 billion kilometers. That distance equals roughly 213 astronomical units. Remember that 1 astronomical unit is the distance between Earth and the Sun. Pluto orbits at about 39 astronomical units. So at 20 kilometers per second, a person could travel well beyond Pluto within a lifetime. They would pass through the Kuiper Belt and continue outward. They might approach the inner regions of the Oort Cloud, which is believed to begin somewhere between 2,000 and 5,000 astronomical units from the Sun. However, even after 50 years at 20 kilometers per second, they would remain far inside that distant halo. Now let us raise the speed to 50 kilometers per second. Over 50 years, that steady cruise would cover about 80 billion kilometers. That equals roughly 533 astronomical units. At this speed, a traveler would move far beyond the Kuiper Belt. They would reach a region of space that few spacecraft have ever approached. Yet even at 533 astronomical units, the inner Oort Cloud would still lie thousands of astronomical units away. Now consider 150 kilometers per second. Over 50 years, that speed it would carry a spacecraft about 240 billion kilometers. That equals roughly 1,600 astronomical units. this begins to approach the lower estimates of the inner Oort Cloud. It represents a dramatic expansion of reach compared to today's cruise speeds. Even so, the outer edge of the Oort Cloud may extend up to 100,000 astronomical units from the Sun. Now we step into the light fraction benchmarks. At 0.1% of light speed, or 300 kilometers per second, a spacecraft would travel about 475 billion kilometers in 50 years. That equals roughly 3,167 astronomical units. At this speed, a traveler could move deep into the inner Oort Cloud. The Sun would appear as a bright star behind them, yet they would still remain far from the nearest true star system. Finally, consider 1% of light speed, or 3,000 kilometers per second. Over 50 years, a spacecraft would travel about 4.7 trillion kilometers. That equals roughly 31,600 astronomical units. At this speed, the traveler would approach the outer regions of the Oort Cloud. They would be traveling nearly halfway to 1 light year. Since 1 light year equals about 63,000 astronomical units, even 1% of light speed for 50 years would not quite reach that mark. And Alpha Centauri sits about 4.37 light years away. That equals roughly 275,000 astronomical units. Even at 1% of light speed, reaching the nearest star would require more than 400 years. This calculation reveals something steady and clear. Within a single lifetime, using realistic cruise speeds, we can explore the outer solar system. We can pass beyond Pluto. We can even enter the distant shell of icy bodies surrounding the Sun. However, reaching another star remains beyond that boundary. The gap between tens of thousands of astronomical units and hundreds of thousands is immense. Now let us consider round-trip travel. If someone wished to go out and return within 50 years, their maximum radius would be cut in half. At 20 kilometers per second, a round trip would allow travel to about 16 billion kilometers outward before turning back. At 50 kilometers per second, the round-trip radius would be about 40 billion kilometers. At 150 kilometers per second, about 120 billion kilometers. Each scenario reduces reach significantly when return is required. This is the quiet truth of lifetime travel. Outward journeys can stretch far. Round trips shorten the horizon. The need to come home changes the boundary. A lifetime frames our ambition gently. It shows that the outer solar system lies within reach. It shows that the Oort Cloud begins to emerge at higher speeds. And it shows that the stars remain beyond the span of one human life, even at speeds far greater than we currently possess. When distance is multiplied by 50 years, the solar system begins to feel navigable. Beyond that, time stretches into centuries and millennia. A lifetime turns space travel into a boundary line that is both inspiring and humbling. Deep space feels empty, and that emptiness changes how motion works. On Earth, cars slow down when engines turn off because of friction and air resistance. In space, there is almost no friction. Once a spacecraft reaches a certain speed, it keeps moving at that speed, unless something pushes or pulls on it. This is one of the most important ideas in space travel. Most of the speed a spacecraft will ever have is given to it near the beginning of its journey. The launch phase is loud and powerful. After that, the trip becomes quiet and steady. When a rocket lifts off, It burns large amounts of fuel in a short time. The goal is to escape Earth's gravity and then shape a path around the Sun. Once that path is set, the engines usually shut down. From that point forward, the spacecraft mostly coasts. Coasting does not mean slowing down. It means continuing at the same speed in the same direction. Small correction burns may occur to adjust the path, but these burns are tiny compared to the initial launch. Voyager is a clear example. It received its main push in the late 1970s. After gravity assists from Jupiter and Saturn, it reached its outward speed. For decades since, it has simply continued moving through space. It does not fire large engines. It drifts steadily outward. This pattern appears again and again. New Horizons was launched at high speed and received a boost from Jupiter. After that, it coasted most of the way to Pluto. Ion engines, like those used on the Dawn spacecraft, are different because they apply small thrust over long periods. But even then, total acceleration remains limited. The reason for this coasting reality is tied to fuel. Rockets must carry their fuel with them. That fuel adds mass. To push fuel, you need more fuel. This creates a cycle where increasing speed requires exponentially more propellant. This idea is captured in what is called the rocket equation. The rocket equation shows that to achieve large increases in velocity, a spacecraft must carry much more fuel than payload. The faster you want to go, the more fuel you must bring. Imagine a spacecraft that wants to double its speed. It may need several times its own mass in fuel to do so. To triple its speed, the fuel requirement grows even more dramatically. At some point, the mass of fuel becomes too large to lift from Earth. This is why chemical rockets provide a powerful but short burst of acceleration. They are efficient near launch, where gravity is strongest. After that, carrying extra fuel for large mid-course burns becomes inefficient. Even nuclear thermal propulsion, which promises higher efficiency than chemical rockets, still faces this fuel mass problem. The physics remains the same. More speed requires more propellant mass. Because space has very little resistance, there is no need to keep burning fuel just to maintain speed. Once you reach cruise velocity, you keep it. That is why missions are designed to get as much velocity as possible early on. Gravity assists are used to increase speed without burning extra fuel. When a spacecraft swings around a planet, it can gain energy from that planet's motion. This technique helps overcome some limits of fuel mass. But it depends on planetary alignment and cannot be repeated endlessly. So most deep space missions follow the same pattern. A strong launch, possibly 1 or 2 gravity assists, then decades of steady coasting. This quiet drift defines how far we can go. If we want to reach greater distances within a lifetime, we must achieve higher cruise speeds early in the mission. After that, the spacecraft simply carries that speed forward. Coasting also reveals why sustained high acceleration is rare. Continuous thrust over long periods would require either enormous fuel reserves or highly efficient propulsion systems with external power sources. Most current missions cannot provide that for decades. So when we picture a spacecraft traveling to the outer solar system, we should not imagine engines roaring the whole way. We should imagine a silent object gliding through darkness, moving steadily at a speed it gained long ago. This is the coasting reality. space travel is less about constant motion and more about one decisive push. The distance we reach is determined by how much speed we can give ourselves at the start. After that, we drift patiently into the vastness. The sun does not end where its light fades. It fills space with a steady outward flow of charged particles. This stream is called the solar wind. It spreads outward in all directions, creating a vast bubble around our solar system. This bubble is known as the heliosphere. It is not solid, and it has no sharp wall. Instead, it is a region where the sun's influence dominates the surrounding space. Inside the heliosphere, the solar wind pushes against the thin gas that exists between the stars. Beyond that region lies the interstellar medium. This is the space between stars. It is not empty, but it is extremely thin. The heliosphere marks the transition between our sun's environment and the broader galaxy. The size of the heliosphere changes over time. It responds to the strength of the solar wind and the pressure of interstellar space. But we have an approximate distance for its boundary. Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, in 2012. At that time, it was about 121 astronomical units from the Sun. Voyager 2 crossed in 2018 at about 119 astronomical units. To understand what that means, remember that 1 astronomical unit equals the distance between Earth and the Sun. Pluto orbits at about 39 astronomical units, so the heliosphere extends roughly 3 times farther than Pluto's orbit. At Voyager's steady outward speed of about 17 kilometers per second, it took more than 35 years to reach that boundary. Voyager was launched in 1977. It crossed into interstellar space in 2012. If we use our benchmark speeds, we can imagine reaching that boundary more quickly. At 20 kilometers per second, the heliopause would be reached in about 28 years. At 50 kilometers per second, it would take about 11 years. At 150 kilometers per second, the journey would take less than 4 years. At 0.1% of light speed, it would take under 2 years. At 1% of light speed, it would take only a few months. These numbers show that leaving the heliosphere is not beyond reach within a lifetime. Even with present-day cruise speeds, crossing that boundary is possible within decades. But crossing the heliosphere does not mean leaving the solar system entirely. The gravitational reach of the Sun extends much farther than the solar wind bubble. The Oort Cloud, which may stretch up to 100,000 astronomical units from the Sun, remains bound by gravity. So when Voyager crossed the heliopause, it entered interstellar space in terms of plasma environment. Yet it still remains deeply within the Sun's gravitational influence. It is still orbiting the center of the galaxy along with the Sun. The heliosphere can be thought of as the shoreline of our star's atmosphere. Crossing it is like stepping out of a warm current into colder water. The density of particles changes. The magnetic environment shifts. Voyager detected this change directly. Instruments measured differences in particle density and magnetic fields. The crossing was not marked by a visible wall, but by a subtle shift in environment. If we imagine a human lifetime journey, reaching the heliosphere could be a meaningful milestone. It would mark the transition from solar wind dominance to the broader interstellar medium. At 20 kilometers per second, this crossing might occur near the end of a 30-year outward journey. At higher speeds, it could occur much earlier. The Sun's bubble is large, but it is finite. Beyond that boundary lies true interstellar space. Yet even there, the nearest star remains thousands of times farther away. The heliosphere sits at about 120 astronomical units. Alpha Centauri lies about 275,000 astronomical units away. This comparison shows scale clearly. Leaving the heliosphere is achievable within a lifetime. Reaching another star is not, using today's technology. The heliosphere is both a boundary and a beginning. It marks the edge of the Sun's breath. It also marks the start of the much larger ocean between stars. Crossing that shoreline would be a historic moment for any traveler. But beyond it, the journey stretches into distances that dwarf the first 100 astronomical units. Even the solar system has a shoreline you can cross. But the sea beyond remains vast, patient, and measured not in decades, but in centuries and beyond. Past the giant planets, the solar system does not suddenly end. It widens, it thins, it becomes colder and darker, but it continues outward in a broad, distant region known as the Kuiper Belt. The Kuiper Belt is a wide ring of icy bodies that begins just beyond Neptune, around 30 astronomical units from the Sun. It stretches outward to about 50 astronomical units, and perhaps slightly beyond. It is not a tight ring like Saturn's rings. It is more like a deep outer shell filled with scattered, frozen objects. Pluto lives within this region, but Pluto is not the edge. It is only one of many icy worlds. There are thousands of Kuiper Belt objects that have been identified, and likely millions that are too small or too faint to see clearly from Earth. Many of these objects are remnants from the early solar system. They are made mostly of ice and rock. They move slowly around the Sun in long, distant orbits. Some of them take hundreds of years to complete a single trip around the Sun. When we passed Pluto in 2015 with the New Horizons spacecraft, it felt like we had reached the outer limit of the known planetary system. But in truth, we had only begun to enter the Kuiper Belt. Let us imagine traveling through this region at our benchmark speeds. At 20 kilometers per second, reaching 40 astronomical units would take about 19 years. That is roughly how long it took Voyager to pass Pluto's orbit. At 50 kilometers per second, that same distance could be reached in about 8 years. At 150 kilometers per second, it would take less than 3 years. These speeds begin to compress what once felt like generational missions into decade-long journeys. But once inside the Kuiper Belt, distances continue to grow. Traveling from 40 astronomical units to 50 astronomical units may require several more years at lower speeds. The region is not a single target. It is a wide band. As travel time stretches, power becomes a concern. Solar panels lose efficiency as sunlight weakens. At Pluto's distance, sunlight is about 1,600 times weaker than at Earth. Beyond that, solar power becomes impractical for large spacecraft. This is why Voyager and New Horizons rely on radioisotope thermoelectric generators. These devices convert heat from radioactive decay into electricity. They provide steady power for decades, but they also slowly weaken over time. Navigation also becomes more delicate. Far from the Sun, gravitational influences are weaker and more subtle. Small course corrections must be planned carefully. Communication delays grow longer as distance increases. At 40 astronomical units, radio signals take about 5.5 hours to travel one way. At 50 astronomical units, the delay approaches 7 hours. Every instruction sent from Earth must wait hours for confirmation. Inside the Kuiper Belt, space feels quiet and wide. Objects are spread across millions of kilometers. The region is not densely packed like an asteroid field in a movie. It is spacious and mostly empty, but with icy worlds scattered across its breadth. For a lifetime traveler moving outward at 20 kilometers per second, the Kuiper Belt would occupy decades. At higher speeds, it could be crossed within a handful of years. Yet even at 150 kilometers per second, the outer solar system still demands patience. Pluto stands as a signpost, not a wall. Beyond it, the sun still shines, though dimly. The solar wind still flows, though more gently. The gravitational pull of the sun still holds sway. The Kuiper Belt represents the long outer shelf of our planetary neighborhood. It shows that the solar system is not just a cluster of planets. It is a layered structure, with rings and reservoirs extending far beyond the bright inner worlds. Travel through this region feels different from travel between inner planets. Distances stretch into tens of astronomical units. Communication delays become routine. Power generation shifts away from sunlight. The outer solar system is wide, slow, and quietly crowded with frozen remnants of its birth. Crossing it within a lifetime is possible at higher speeds. But even then, it reminds us that the sun's reach extends far beyond the planets we memorize in school. If the Kuiper Belt is the outer shelf of the solar system, the Oort Cloud is something much larger and more distant. It is not a ring. It is not flat. It is believed to form a vast spherical halo surrounding the sun. The Oort Cloud has never been seen directly. It is too far and too faint for current telescopes to observe clearly. Its existence is inferred from the paths of long-period comets. These comets appear to fall inward from extremely distant regions, far beyond Pluto and the Kuiper Belt. Scientists estimate that the inner edge of the Oort Cloud may begin somewhere between 2,000 and 5,000 astronomical units from the Sun. The outer edge may extend as far as 100,000 astronomical units. To understand that scale, remember that Pluto orbits at about 39 astronomical units. The heliosphere ends around 120 astronomical units. The inner Oort Cloud begins tens of times farther than that. Now let us imagine traveling to the inner edge of the Oort Cloud at our benchmark speeds. At 20 kilometers per second, covering 2,000 astronomical units would take roughly 470 years. That is nearly half a millennium. At 50 kilometers per second, the journey would take about 190 years. At 150 kilometers per second, about 63 years. Even at that high speed, reaching the inner Oort Cloud begins to stretch beyond a typical lifetime. If we imagine traveling at 0.1% of light speed, or 300 kilometers per second, reaching 2,000 astronomical units would take about 31 years. At 1% of light speed, it would take only about 3 years. These differences show how dramatically speed changes our reach. At today's cruise speeds, the Oort Cloud lies far beyond a human lifetime. At light fraction speeds, it becomes more approachable. Now consider the outer edge, at perhaps 100,000 astronomical units. At 20 kilometers per second, reaching that distance would take nearly 24,000 years. At 50 kilometers per second, about 9,500 years. At 150 kilometers per second, about 3,200 years. Even at 0.1% of light speed, the journey would take more than 1,500 years. At 1% of light speed, it would take about 150 years. The outer Oort Cloud remains far beyond the span of a single life, even at extraordinary speeds. Life in the Oort Cloud would feel profoundly distant from Earth. At 2,000 astronomical units, a radio signal would take about 11 days to travel one way. A conversation would stretch into weeks between messages. At 10,000 astronomical units, the delay grows to nearly 2 months one way. At 100,000 astronomical units, signals would take about 1.5 years to reach Earth. Communication would no longer feel immediate. It would become a rhythm measured in seasons. The sun itself would appear very different from those distances. At 2,000 astronomical units, it would look like a bright star. At 100,000 astronomical units, it would shine like one of many bright points in the sky, no longer dominant. The Oort Cloud represents the far gravitational halo of our solar system. Objects there are only weakly bound to the sun. A passing star could disturb them. Galactic tides can slowly shift their orbits. For a traveler, reaching the inner Oort Cloud at 150 kilometers per second might just fit within a long lifetime. But returning home would double the required time. A round trip would exceed a century. This reveals a gentle truth. The Oort Cloud belongs to the Sun, yet it lies closer in spirit to interstellar space than to the planets. It is the far fog bank of our system. Even at our most ambitious near-term speeds, only its inner regions lie within possible reach of a single lifetime. Its outer reaches stretch into timespans that feel geological rather than human. At Oort distances, the Sun becomes just one bright star among many. The solar system fades into a background presence, and distance itself begins to feel less like a number and more like a quiet separation measured in years of silence. Speed tells us how far we can go, but speed alone does not decide whether we can survive the journey. A spacecraft carrying instruments is one thing. A spacecraft carrying people is something very different. Deep space is not empty in a gentle way. It is filled with radiation. High-energy particles from the Sun and from distant cosmic events move constantly through space. Earth's magnetic field protects us from much of this radiation. Once we leave that shield, exposure increases. Short missions beyond Earth orbit, such as trips to the Moon, expose astronauts to more radiation than they would receive on Earth. Longer missions, such as a journey to Mars, would increase that exposure further. Over years, radiation can damage cells. It can raise cancer risk. It can affect the nervous system and other organs. Shielding can help, but shielding adds mass. And adding mass makes propulsion more difficult. Beyond radiation, there is the question of life support. humans need air, water, and food. For a mission lasting months, these supplies can be carried from Earth. For a mission lasting decades, carrying everything becomes impractical. This leads to the idea of closed-loop living. A closed-loop system recycles air, water, and waste. Carbon dioxide is removed from the air, and oxygen is regenerated. Water is purified and reused. Waste materials are processed. The International Space Station already uses partial recycling systems, but a multi-decade mission would require near-complete recycling. The system would need to operate reliably for years without replacement parts from Earth. Food presents another challenge. Stored food can last for a limited time. Growing food in space would require lighting, water, nutrients, and careful environmental control. Agriculture becomes part of the spacecraft itself. Health is another factor. In microgravity, bones lose density, muscles weaken, the heart adjusts to the lack of gravity. Astronauts on the space station exercise daily to reduce these effects. For missions lasting years, artificial gravity might be necessary. One way to create artificial gravity is by rotating the spacecraft. Rotation can produce a centrifugal force that mimics gravity, but building such a structure adds complexity and mass. Psychological limits also matter. Isolation in deep space would be profound. Communication delays would grow as distance increases. At Jupiter, signals take tens of minutes to travel one way. In the Oort Cloud, they take days or weeks. Crew members would need to function independently. They would not receive immediate guidance from Earth. Over decades, separation from home would feel permanent rather than temporary. Maintenance becomes another issue. Machines wear down, systems break. On Earth, parts can be replaced. In deep space, the crew must carry spare parts or manufacture them on board. Reliability becomes critical. Energy is also a constraint. Solar panels become less effective far from the sun. Nuclear power sources can provide steady electricity, but they must operate safely and continuously for decades. Even simple medical issues become serious concerns. A broken bone, infection, or chronic illness could become life-threatening far from Earth. Medical supplies and training would need to cover a wide range of possibilities. When we think about traveling for 50 years at 20 or 50 kilometers per second, the engineering challenge is not only propulsion. It is sustaining a small, isolated environment for decades. A spacecraft carrying humans becomes more than a vehicle. It becomes a moving home. It must provide air, water, food, protection, medical care, and psychological stability. These requirements add mass. More mass requires more energy to accelerate. The relationship between human needs and propulsion physics becomes tightly linked. This is why robotic missions reach farther than crewed missions. Probes do not need air or food. They do not need shielding against long-term radiation in the same way. They can endure isolation without emotional strain. So when we ask how far we could travel using the latest technology, we must separate robotic reach from human reach. Robotic spacecraft can drift outward for decades with minimal support. Human spacecraft must carry an entire life support ecosystem with them. A crewed ship is not just a moving object. It is a closed world traveling through darkness. Its limits are not defined only by speed, but by biology and time. In the end, propulsion may carry us outward, but survival systems decide whether that outward journey can include us. And those systems quietly shape how far humanity itself can truly go. Some future propulsion systems do not aim to break the laws of physics. They aim to stretch what we already understand. Instead of inventing something completely new, they improve efficiency, temperature, and endurance. These changes may seem small, but in space travel, small margins matter. One of the most discussed upgrades is nuclear thermal propulsion. In a chemical rocket, fuel burns and produces hot gas. That gas expands through a nozzle and creates thrust. The temperature of that gas limits how fast it can leave the engine. In a nuclear thermal rocket, the propellant is heated by a nuclear reactor instead of chemical combustion. Hydrogen gas passes through a reactor core and becomes extremely hot. The hotter the gas, the faster it expands out of the nozzle. This higher temperature means higher exhaust velocity. Higher exhaust velocity means better efficiency. Engineers measure this using something called specific impulse. Nuclear thermal propulsion could nearly double the efficiency of chemical rockets. What does that mean in practice? It means a spacecraft could carry less propellant for the same mission, or it could carry more payload while keeping total mass manageable. It could also reach higher cruise speeds after launch. For missions to Mars, nuclear thermal propulsion could shorten travel time. Instead of 6 to 9 months, the trip might take 3 to 4 months. Shorter travel time reduces radiation exposure and life support strain. For outer planet missions, nuclear thermal engines could allow heavier spacecraft to depart Earth with greater initial velocity. They would not create light-speed travel, but they could move the benchmark from 20 kilometers per second toward higher steady cruise speeds. Another concept is nuclear electric propulsion. In this system, a nuclear reactor generates electricity. That electricity powers electric engines, such as ion thrusters. Ion engines are very efficient, but they require steady electrical power. Solar panels work well near Earth. Far from the sun, sunlight weakens. A nuclear reactor could provide consistent power regardless of distance. With nuclear electric propulsion, a spacecraft could apply small but continuous thrust for years. Over long durations, that steady acceleration could build significant total velocity change. The thrust remains low compared to chemical rockets, but over time, it adds up. This approach works especially well for cargo missions or robotic probes that do not require rapid acceleration. In terms of our benchmark speeds, nuclear systems might help push steady cruise speeds closer to 50 or even 100 kilometers per second for certain missions. That would dramatically shorten travel times to the outer solar system. However, these systems are still under development. Ground tests of nuclear thermal engines have been performed in the past. New research programs aim to test them again. Nuclear electric systems remain mostly conceptual for large spacecraft. Those small electric engines are already operational. Even with these upgrades, the basic physics does not change. The rocket equation still applies. More speed still requires more energy. Nuclear systems improve efficiency, but they do not remove mass constraints. For a 50-year lifetime journey, increasing cruise speed from 20 to 50 kilometers per second can more than double reachable distance. that margin matters. It could mean reaching deeper into the Oort Cloud, rather than remaining near the Kuiper Belt. For Mars missions, shaving months off travel time reduces radiation exposure and psychological strain. For Jupiter missions, it could turn multi-year travel into something shorter and more manageable. Near-term propulsion upgrades do not promise interstellar travel. They do not close the gap to Alpha Centauri, but they do stretch the solar system inward. They make more of it accessible within decades instead of generations. In space travel, improvements of 2 or 3 times efficiency are significant. They change payload mass, mission design, and reachable distance. Nuclear propulsion may not rewrite physics, but it shifts the margins. And in a universe measured in decades and astronomical units, margins matter. Near-term propulsion changes do not transform the map entirely, but they redraw its boundaries gently. And even gentle shifts can open new regions of the solar system to human reach within a lifetime. Stars look close in the night sky. They appear like small points scattered across a dark background. But their distance is not measured in millions or billions of kilometers. It is measured in light years. The nearest star system, Alpha Centauri, lies about 4.37 light years away. 1 light year equals about 9.5 trillion kilometers. That means Alpha Centauri is roughly 41 trillion kilometers from Earth. If we traveled at Voyager's steady outward speed of about 17 kilometers per second, reaching Alpha Centauri would take more than 75,000 years. Even at 20 kilometers per second, the journey would still take tens of thousands of years. At 50 kilometers per second, the trip would take around 26,000 years. At 150 kilometers per second, it would still take nearly 9,000 years. These numbers stretch far beyond human history. Now imagine traveling at 0.1% of the speed of light, or 300 kilometers per second. At that speed, reaching Alpha Centauri would take about 4,300 years. Even this significant increase leaves the journey far beyond a single lifetime. At 1% of light speed, about 3,000 kilometers per second, the travel time drops to roughly 430 years. That begins to feel like a long chapter of civilization, rather than geological time. But it still exceeds the span of a human life. Some proposals imagine speeds of 10% of light speed. At that velocity, Alpha Centauri could be reached in about 44 years. But accelerating a large spacecraft to that speed would require enormous energy. The energy needed to move a 100-ton spacecraft to 10% of light speed would exceed the total annual energy production of many nations combined. There are also physical hazards. At interstellar speeds, even tiny dust grains become dangerous. A speck of dust striking at thousands of kilometers per second carries tremendous energy. Shielding against such impacts adds mass, which increases propulsion demands. Radiation also changes at these speeds. Cosmic rays and interstellar particles would strike the spacecraft with higher relative energy. Long-duration exposure would require advanced shielding and careful engineering. One concept that approaches interstellar speed is the breakthrough Starshot proposal. It suggests using powerful Earth-based lasers to push a tiny sail attached to a gram-scale probe. The goal would be to accelerate the probe to about 20% of light speed. At that speed, A tiny probe could reach Alpha Centauri in about 20 years. But this idea remains experimental. It requires enormous laser arrays and precision engineering. It is not operational technology today. It also applies only to extremely small spacecraft. A human crewed vessel at that speed would require energy and shielding far beyond current capabilities. This comparison reveals the boundary clearly. Within a single lifetime, using present or near-term technology, we can explore the outer solar system. We can cross the heliosphere. We may even enter the inner Oort Cloud at higher speeds. But reaching another star remains outside the limits of our current tools. The gap between hundreds of astronomical units and hundreds of thousands is immense. This does not mean interstellar travel is impossible in principle. Physics allows motion at a fraction of light speed, but the engineering and energy requirements create a different category of challenge. The solar system is one ocean. Interstellar space is another. The distances between stars require speeds and energy far beyond what we can sustain for large spacecraft today. So how far could we travel using the latest technology? We could leave Earth. We could cross the orbits of the planets. We could move beyond Pluto. We could cross the sun's bubble and drift into interstellar space. Within a lifetime, we could reach the far outer regions of our own solar system. We could stand at the shoreline of the sun's influence and look outward. But the stars themselves remain distant lights. They are visible every night, yet separated from us by centuries of travel even at ambitious speeds. The boundary is not a wall. It is a measure of time. With today's tools, our reach extends across the solar system. Beyond that, the universe waits patiently, measured not in days or years, but in centuries of motion through the dark.